8, 7, 6, 5, 4, 3, 2, 1.
When you look up at the sky on a clear night, you will see a multitude of stars. While it is incredible that some of them are trillions of miles away, scientists are excited about something else that is even further away. Thanks to the new James Webb Space Telescope, they have sighted something massive lurking at the very edge of the universe. What have scientists discovered? How did the JWST assist in discovering it? And can the object have any effect on our planet? Join us as we dive into the massive object that the James Webb Space Telescope just discovered hiding at the edge of the universe. Have you ever wanted to complete a task but wished you had the proper tools? Perhaps you wanted to geek on your smartphone but lacked the precision tools to crack it open, or badly need a flamethrower. Scientists worldwide were once in that position until the launch of the James Webb Space Telescope. The universe contains a lot of mysteries that scientists are trying to unravel. One of the most puzzling is the question of how the universe itself started. While there are many hypotheses, they still need to be proven, and the proof centers on one thing: finding out exactly what happened at the beginning of the universe. That is no small feat, as it requires the best equipment humankind has ever made. The tool must be able to see the edge of the universe to study some of the oldest objects or formations in existence. Some of these objects have existed for billions of years, and it's time to demystify them. This is where the JWST comes in. The JWST is simply the most powerful telescope humans have ever dreamed up. The father of the telescope, Galileo Galilei, must be proud of how far we have brought his craft. However, that progress comes at a steep price, $10 billion, and with a lot of panicky moments during the launch. Since everything has gone well with the launch and setting up of the JWST in its permanent orbit, NASA can sit back and enjoy the massive scientific returns from the massive space observatory, and the JWST has been delivering. In the short time scientists have had a go at it, the JWST has revealed truly shocking things about our universe, many of which the scientists didn't see coming. At this rate, it is not an exaggeration to say the JWST will challenge everything we thought we knew about the universe. Just as expected, the JWST is already taking us far back into the past and nearer to the edge of the universe. Scientists call this part of the time a glimpse of the early universe. This is due to its ability to detect the faint light of incredibly distant galaxies as they glow in infrared light, a wavelength that is invisible to the human eye. As such, the image we are talking about here has been helping astronomers to better understand how galaxies formed and evolved in the early days of the universe. The image that has excited scientists captured a galaxy cluster MAX 0647 as well as the distant galaxy MAX 0647JD. The cluster appears as a dazzling grouping of galaxies that shine like precious gems against the dark backdrop of space. The distant galaxy is visible thanks to a certain type of observational phenomenon due to the cluster. This phenomenon is called gravitational lensing, and it occurs when galaxies in the foreground act like magnifying glasses, allowing us to see the more distant objects behind them. Small boxes were used to pinpoint the galaxy MAX 0647JD, and more detailed images of the galaxy are aligned along the right side of the image. The cluster essentially triple lensed the galaxy, magnifying it and causing it to appear in 3 separate places within the image. Each box on the right showcases different details of the galaxy. While MAX 0647JD was discovered 10 years ago using the Hubble Space Telescope, it took the JWST not long to reveal something surprising about the cluster. There are 2 features. Here is what happened. Using the Hubble, it was just the pale red dot. We could tell it was really small, just a tiny galaxy in the first 400 million years of the universe. However, with the powerful JWST, scientists were able to resolve 2 objects. However, a puzzle remains. Are these 2 galaxies or 2 clumps of stars within a galaxy? They don't know yet, but guess what they are banking on to get the answers? The JWST. These are not even the most distant objects the JWST has discovered. That honor goes to one of the earliest galaxies formed not long after the Big Bang. This particular galaxy was captured at about only 350 million years after the Big Bang, or after the universe began. The galaxy called Glass Z12 and another galaxy formed about 450 million years after the Big Bang was found not long after the powerful Space Observatory began its infrared observations of the cosmos. Before this, the earliest galaxy observed was GNZ11, which existed 400 million years after the Big Bang and was spotted by the Hubble Space Telescope in 2016. In fact, the scientists using the JWST said as soon as they started taking data, they came to the realization that there were many more distant galaxies than they were expecting. Basically, the universe produced galaxies faster and earlier than the researchers thought. Just a few 100 million years after the Big Bang, there were already lots of galaxies. The JWST has just opened up a new frontier, giving us a front-seat view that helps us better understand how it all began. Both galaxies have a sphere or disc-like shapes, but in size, they are just a tiny percentage of the size of the Milky Way galaxy. The two galaxies are very distant from us, but they are extremely bright and generate stars very rapidly. Further research has suggested that galaxies may have begun popping up in the universe just 100 million years after the Big Bang, which took place 13.8 billion years ago. This timeline challenges the theories astronomers have propounded about how and when the first galaxies formed. The puzzling thing was that the early universe was undeniably chaotic and crowded, but the structure of the two galaxies turned out to be calm and orderly. Do you know one other thing that has baffled these scientists? It is the sheer amount of brightness in these two galaxies. One possibility is that the galaxies were massive and contained a lot of low-mass stars, which is similar to the types of galaxies that formed later on in the universe. Another possibility is actually the opposite, smaller galaxies with fewer but extremely bright stars. These luminous objects, which scientists call population 3 stars, have long been theorized as the first stars ever born in the cosmos. The first stars in the universe are believed to have been blazing hot and comprised of hydrogen and helium. The stars that came afterwards must have contained heavier elements that were created when the first stars exploded. So far, no population 3 stars have ever been spotted within our local universe. But scientists are banking on powerful telescopes like the JWST that can peer back into the distant universe, effectively looking back in time to see the first population 3 stars one day. It won't be surprising if the older of the two galaxies, Glass Z12, contains population 3 stars. The JWST continues to destroy records set by former telescopes, and the surprising thing is that it's doing so within the short time that it's begun fully functioning. While you might be appropriately wowed by the two distant objects already mentioned, there is even more, like the galaxy candidate Sears 93316. This object formed about 250 million years after the Big Bang and set a record redshift of Z 16.7. This discovery is a massive deal, demonstrating the power of the beast developed and launched by NASA. SEERS stands for Cosmic Evolution Early Release Science Survey. It is a special program meant for imaging with JWST. Researchers will confirm the redshift with follow-up observations using spectroscopy. This is why they still refer to it as a galaxy candidate. However, the study has already determined that Sears 93316 can't be a low-mass star or an unobstructed active galactic nucleus. This is based on imaging data from the NIRCam, JWST's primary imager. After the Big Bang took place, the universe entered what is known as the Dark Ages. This is the time before any of the stars you see today were born. However, the observations of this galaxy push observations back to the time when scientists thought the first galaxies ever to exist were being formed. NASA says the JWST can detect galaxies at redshifts greater than 20, which correspond to less than 200 million years after the Big Bang. However, the fact is that these galaxies will likely be extremely hard to find. But with the detection of Sears 93316, scientists hope that they may exist. Now, if you have been baffled by redshift and shifted light, here is what they mean. Following the Big Bang, the universe was like a hot soup of particles like protons, neutrons, and electrons. However, as the universe began to cool, the protons and neutrons began combining into ionized atoms of hydrogen and some helium. In these ionized form, the atoms of hydrogen and helium attracted electrons, turning them into neutral atoms. This allowed light to travel freely for the first time in the universe, as the light was no longer scattering off free electrons. This was a turning point in the universe, as for the first time ever, it was no longer opaque. But wait, it would take some time, maybe a few 100 million years after the Big Bang, before the first sources of light would start to form, bringing to a close the pages of the cosmic dark ages. So this is quite interesting, as it means the universe was ready to transmit light before the sources of light were formed. So what did the universe's first light, that is, the stars that fuse the existing hydrogen atoms into more helium, look like? We don't know that yet. And when exactly did these first stars form? We don't know that either. Again, these are questions scientists are waiting for the JWST to answer. But what about shifted light? Well, imagine light leaving the first stars and galaxies nearly 13.6 billion years ago and traveling through space and time to reach our telescopes. What this means is that we are seeing these objects as they were when the light first left them 13.6 billion years ago. However, by the time this light gets to us, its color or wavelength would have been shifted towards the red, something called a redshift. In this particular case of very distant objects, Einstein's general relativity applies. It says because the universe expands, the space between objects actually stretches, causing objects to move away from each other. Furthermore, any light in that space will also stretch, and the light's wavelength will shift to longer wavelengths. This can make distant objects very dim or invisible at visible wavelengths of light because that light reaches us as infrared light. So when they say redshift, it means that light that is emitted by these first stars and galaxies as visible or ultraviolet light actually gets shifted to redder wavelengths by the time we see it from the Earth. For very high redshifts, that is, the farthest objects from us, that visible light is generally shifted into the near and mid-infrared part of the electromagnetic spectrum. For that reason, to see the first stars and galaxies, we need a powerful near and mid-infrared telescope, which is exactly what Webb is. Another distant object that the JWST has clarified is what is popularly called the Pillars of Creation. This was first captured by Hubble in 1995. While it was impressive at the time, the JWST has done it far better. The three-dimensional pillars resemble rock formations but are very permeable. The columns comprise cool interstellar gas and dust that sometimes appears semi-transparent in near-infrared light. Thanks to the images taken in 1995 and 2014, JWST's new image of the Pillars of Creation will assist researchers in improving their models of how stars formed by identifying far more precise counts of newly formed stars, along with the quantities of gas and dust in the region. With time, scientists will gain a clearer understanding of how stars form and burst out of these dusty clouds over millions of years. The second time the JWST took an image of the Pillars of Creation, it used the mid-infrared instrument or MIRI. The result was a somber and chilling production. Another one in the set of images showed the Nebula 30 Doradus in great detail. It is also known as the Tarantula Nebula and is one of the largest and brightest star-forming regions in the galaxies nearest to our Milky Way. The Tarantula Nebula is located 161,000 light-years away in the Large Magellanic Cloud Galaxy. The name is inspired by the long dusty filaments resembling spiders' legs in older images. The picture shows the stellar nursery in another level of clarity, showing tens of thousands of young stars that were previously shrouded in cosmic dust, hence never seen before. Often referred to as the successor of the Hubble Space Telescope, the JWST is the largest space observatory ever built. Its gigantic sunshield base measures a massive 22 meters by 12 meters, about the size of a tennis court. However, even though it is nearly twice as big as Hubble, which is only 13 meters long, the JWST is almost half by weight at only 6,500 kilograms. The JWST's gold-plated mirrors have a total diameter of 6.5 meters, much larger than Hubble's 2.4-meter diameter plate. This means the JWST will have approximately a 15 times wider view than Hubble. You've heard different comparisons of JWST with Hubble, but the two iconic telescopes function differently. The Hubble's primary focus is on both visible and ultraviolet light. It has some infrared capability, but it is nowhere near the extent to which the JWST can. In fact, the JWST is designed to work on the infrared spectrum. This means it can't see in ultraviolet light as the Hubble, but it can focus on bright objects like very distant galaxies. But distant galaxies are not the limit for JWST. It can observe objects that are over 13.6 billion light-years away. This means we will look back 13.6 billion years, which brings us between 100 and 215 million years close to the Big Bang. Most of the size of the JWST is due to its large sun shield. It is so big that NASA engineers had to design it to unfold during the launch because of space limitation on the launch vehicle, and then unfurl it while it journeyed to the permanent orbit. This is used on all space telescopes, but is especially important with the JWST due to its infrared cameras. If it isn't kept cool enough, it stands the risk of blinding itself to the lights of objects it is trying to observe. One other key difference between the two satellites is their distance. The Hubble telescope orbited above Earth's atmosphere but was near enough to be approached if repairs needed to be done. But the JWST is many magnitudes further away, around 1.5 million kilometers away. That places it farther than any human can and has ventured, meaning nobody can call on it for a repair if something goes wrong. One of the things scientists have discovered at the very edge of the universe is a galaxy named Able 2744Y1. This galaxy is special for many reasons. Able 2744Y1 is so far away that light from it gets to us after 13 billion years of traveling. Remember, the universe is estimated to be 13.8 billion years old. One thing about Able 2744Y1 is that we are seeing it as it was when it was only 650 million years old. This is true of all distant objects in space because the light from them has taken so long to reach us here on Earth. Able 2744Y1 was discovered using a total of 3 telescopes: Spitzer, Chandra, and Hubble. But just how did 3 telescopes come together to discover a single item? Well, the Hubble captures images in visible and near-infrared light, while the Spitzer has the advantage of using the infrared portion of the electromagnetic spectrum. Scientists use Chandra to collect additional data using X-ray wavelengths. By combining data from these 3 space telescopes, astronomers are able to see galaxies up to 100 times more distant than any of the observatories could have done individually. The astronomers attached to the Instituto de Astrofísica de Canarias (IAC) and La Laguna University in Spain started with the Hubble, which detects the galaxy in question. This is then followed by the Spitzer, whose instruments are used to calculate the distance of the object where it's located. The telescope also helps to determine how many stars are in the galaxy. The scientists also used a method known as gravitational lensing when they photographed Able 2744Y1. The underlying principle is similar to how a magnifying glass bends sunlight, because images from distant galaxies are put into focus by galaxies closer to Earth. This natural telescope to view the most distant objects in the universe was first predicted by Albert Einstein in his general theory of relativity. So how large is this galaxy? Astronomers say Able 2744Y1 is quite small in size. It is about 50 times smaller than our own Milky Way galaxy, or about 2,300 light-years in width. However, what this galaxy lacks in size, it makes up in the rate of star production. It generates stars at a rate 10 times faster than the Milky Way, but that is typical of galaxies in the young universe. The Able 2744Y1 galaxy has a redshift of 8. Redshift is a way of measuring the degree to which an object's light has been shifted to redder wavelengths due to the expansion of the universe. In comparison, the farthest confirmed galaxy before the discovery of Able 2744Y1 has a redshift of more than 7. Remember we said that the universe is 46.1 billion light-years in radius. That is the limit of the observable universe. There is much more out there. How do we know what lies out there beyond the observable universe? We can make inferences based on the laws of physics that we know and by using the things we can measure within our observable universe. For instance, we observe that the universe is spatially flat on the largest scales. It's neither positively nor negatively curved to a precision of 0.25%. If our current laws of physics are correct, we can set limits on how large, at least, the universe must be before it curves back on itself. We can get the best data for our extrapolation from observations from the Sloan Digital Sky Survey and the Planck satellite. The two sources suggest that if the universe does curve back in on itself and close, the part we can see is so indistinguishable from uncurved it must be at least 250 times the radius of the observable part. This leads to the conclusion that the unobservable universe, assuming bearing any topological weirdness, must be at least 23 trillion light-years in diameter. It must contain a volume of space that is over 15 million times as large as the volume we can observe. However, there are compelling arguments that the unobservable universe should be significantly even bigger than that. How? It's like this. The Hot Big Bang might mark the beginning of the observable universe as we know it, but it doesn't mark the birth of space and time itself. This is because before the Big Bang, the universe underwent a period of cosmic inflation. Rather than being filled with matter and radiation and being hot, the universe was filled with energy inherent to space itself, expanding at a constant exponential rate and creating new space so quickly that the smallest physical length scale, the Planck length, would be stretched to the size of the presently observable universe every 10 raised to the power of negative 32 seconds. Sure, inflation stopped in our region of the universe. However, three key questions that directly affect how large our universe is remain unanswered. These questions deal with whether the universe is infinite or not. They are: 1. How big was the region of the universe post-inflation that created our Hot Big Bang? 2. Is the idea of eternal inflation, where the universe inflates eternally into the future in at least some regions, correct? And 3. How long did inflation go on before its end and the resultant Hot Big Bang? It is possible that the universe where inflation occurred barely attained a size larger than what we can observe. Perhaps any year from now, the evidence for an edge to where inflation happened will materialize, and we will have to adjust our perception of the universe again. But it is just possible that there are plenty of universes out there just like ours, following the same laws of physics and having the same types of physical, cosmic structures. This raises the tantalizing possibility of complex life in one of the numerous worlds out there. There should also be a finite size and scale to the bubble in which inflation ended, and an exponentially massive number of such bubbles contained within the larger inflating spacetime. From the most distant galaxy ever captured, we move to another distant object, this time a supernova. What is the most distant supernova ever spotted by astronomers? That title goes to DES 16C2NM. If you are wondering what is up with the name, it is because the supernova was first spotted by the Dark Energy Survey, which is a research work that seeks to better understand the mysterious force thought to be responsible for how the universe's expansion is accelerating. Supernovas are some of the biggest explosions we can ever have. Picture an atomic bomb, but with infinitely more bang. They are like the last valiant effort made by stars before they die. The stars here are at least 5 times bigger than our own sun. Here is how stars work so that we understand how they die. Massive stars basically burn humongous amounts of nuclear fuel at their cores. This leads to the release of tons of energy, and as a result, the center gets very, very hot. This heat generates pressure, and the pressure created by a star's nuclear burning also keeps that star from collapsing. When you see a star in the sky, it's because there's a balance between two opposite forces. On the one side, the star's gravity tries to squeeze the star into the smallest, tightest ball possible. On the other side, the nuclear fuel burning in the star's core produces a strong outward counterpressure. This outward push resists the inward squeeze of gravity. But when the fuel runs out, the star starts to change its behavior. It begins to cool off, causing a drop in pressure. This goes on until gravity eventually wins and the star collapses in a spectacular fashion. This is a brisk affair as the collapse occurs in a short period of time. It would be like the Earth collapsing in just 15 seconds. This collapse creates shockwaves that cause the outer portion of the star to explode. You can also have a supernova when two stars collide. Supernovas are not that common. You could have 2 or 3 in a century, so it is always special when a supernova occurs. DES 16C2NM was detected in 2016, and scientists confirmed a supernova like that is extremely rare. It is like the very extreme version of what you call normal supernovas. The discovery was made by a team of international astronomers, and they say the explosion took place about 10.5 billion years ago. This means the light from the explosion has been traveling to us for more than 3/4 of the existence of the universe itself. What is even more mind-boggling is that the location of the supernova is even more than that, thanks to the expansion of the universe. The team also enlisted the help of 3 powerful telescopes: the Very Large Telescope, Magellan, and the Keck Observatory. It involved more than 400 scientists from all over the world and took 5 years with 525 nights of observation. While the scientists ran into many troubles to locate the supernova, the effort will pay off in many ways. The extreme distance of DES 16C2NM gives the scientific community a totally new insight into the nature of superluminous supernovas, or SLSN. Scientists can determine the amount of metals produced in the explosion by studying the ultraviolet light from the SLSN. It can also reveal the temperature at which the explosion occurs. These 2 things here are key to the understanding of what causes and drives these massive cosmic explosions. However, it may not be long before another, more distant supernova is found, because scientists are out looking for them, spurred on by the extraordinary discovery of DES 16C2NM. What is the furthest astronomical object humans can see? One thing is that there are some objects in the universe that we might never see. Why? About 16 billion light-years from Earth, this marks the current cosmic event horizon of the universe. Are we there yet? Nope, not yet. This distance is the upper limit of light ever reaching us if it originated at that distance today. This implies beyond 16 billion light-years, the expansion of space is faster than the speed of light itself. Obviously, the light will never reach us, as it will have to travel through a relatively expanding space. This also signifies that any event that may have happened today beyond the cosmic event horizon will not be observable by us, no matter what. But we can see even further through telescopes like the JWST. The most distant galaxy ever observed is the GNZ11, located about 32 billion light-years away from Earth. Mind you, we calculate this distance taking into account the expansion of space as well. At about 46 billion light-years away from Earth, we reach what is called the surface of last scattering. This is what you will observe irrespective of the direction you look at. The surface of last scattering is like a uniform sphere of fog from which the first ever photons of cosmic microwave background radiation came after recombination and photon decoupling. Contrary to the name, it's the origin of the very first scattering of light, but the last of what we can observe. Is this finally the edge of the universe? Yes and no. Technically, this is the farthest point in space and the farthest in time that we can observe. That essentially forms the edge of the observable universe. What lies even beyond that is what is known as the opaque universe. This brings us to what is the largest object in the universe? How large is the largest thing? It is so large that it is not supposed to exist. This is because it transcends our perception of size and violates the very laws of physics. The structure is the Hercules Corona Borealis Great Wall. Cosmologists have always been baffled by the uniformity or homogeneity of the universe because the leftover heat from the Big Bang is astonishingly uniform in every direction we look. And because these early temperature fluctuations subsequently led to density fluctuations, one can also say the same thing about the matter in the universe. If the matter in the universe wasn't so smooth and uniformly distributed, large clumps would have attracted smaller chunks of matter, and the universe wouldn't have expanded but instead contracted under its own gravity. However, even though it is homogeneous on a very large scale, the universe, due to slight initial irregularities, is locally heterogeneous. The heterogeneity can be observed in dense populations of stars, galaxies, clusters, a collection of galaxies, and superclusters, a collection of clusters. The homogeneity was explained by the theory of inflation, a highly crucial aspect of the Big Bang model of the universe. This model is currently believed to be the most convincing explanation of the birth of our universe. However, the Hercules Corona Borealis Great Wall is a supercluster that represents such an immense irregularity or non-uniformity that it defies the laws of inflation. The supercluster is so humongous that it exceeds the maximum structural size allowed by the inflationary model of the universe. The Hercules Corona Borealis Great Wall was discovered in 2013 by a team of astronomers while looking for gamma-ray bursts, or GRBs. For this reason, the structure is often called the Great GRB Wall. Gamma rays are the most powerful type of radiation in the entire electromagnetic spectrum. Such super-high-frequency radiation emanates only in a handful of stellar events, such as supernovae, the explosive death of a star, collisions of neutron stars, or matter spun around violently by a black hole. The energy released during a supernova is so colossal that the Sun cannot produce the same amount during its entire lifetime. Astronomers study these bursts because they enable us to locate massive structures in the universe. Massive stars can only form around a dense surplus of mass because that is what they feed on. Also, planetary systems like our solar system are fundamentally congregated debris dispersed during the explosive deaths of these very same stars from supernovae, so studying these structures allows us to glimpse both the childhood and the grand history of our universe. So these researchers recorded an unusually high volume of gamma-ray bursts concentrated about 10 billion light-years away in the direction of the Hercules and Corona Borealis constellations. The angle this volume spanned in space translated to a width of 10 billion light-years. Yes, the Great GRB Wall is 10 billion light-years wide. For perspective, that is 10% of the diameter of the observable universe. The researchers themselves were skeptical about their discovery. How could a single structure account for 10% of the whole observable universe? Co-author John Hackler expressed his disbelief in a press conference in 2014 when he remarked, "I would have thought this structure was too big to exist." However, the team calculated that the chances of the gamma-ray shower springing up randomly in that location are very slim, in fact, far less than 1 in 100. This brought them solace and convinced Hackler to believe that the structure exists. In fact, other structures appear to violate the inflationary model, such as the Sloan Great Wall and the Huge Large Quasar Group. This is why Hackler is adamant that the hype of the Hercules Corona Borealis Great Wall being the largest object won't last for long, because sooner or later, someone is likely to come along and find something bigger, more distant, or older than the thing you found. This period detected by the JWST is known as the Scarcely Probed Era, which explains how the very first stars and galaxies were formed. The events surrounding this process seem partially uncovered by scientists, as the entire process depends on exotic physics. But now that such a discovery has been made about the Big Bang era with the James Webb telescope, cosmologists would be able to dig deeper into more phenomena that have been left unsolved. This involves either confirming the validity of their best consensus models or revealing gaps in understanding that could bring about new discoveries. This ranges from uncertain influences of dark matter and dark energy to the faintly understood feedback between starlight, gas, and dust. Such observations were supposed to take time, as initial projections had estimated that the first galaxies were going to be so small that the JWST might have a hard time finding some of them during its investigations. But the $10 billion powerful telescope proved the predictions wrong and sent astronomers and cosmologists back to work as soon as it sent back its first images of the distant universe. Upon receiving the images, astronomers such as Naidu began to find several galaxies within the images that outshined all predictions about size, age, and luminosity. It was an irregular period that almost made scientists freak out, as Naidu wasn't the only one that made these discoveries. Several research groups also made their discoveries from the images sent back by the JWST. It nearly turned into a field of competition as news of other record-breaking galaxies kept coming from different research groups. It was something scientists never expected. Shortly after the JWST found these galaxies, theorists and observers began to check them out, looking to explain the phenomena. They began to wonder if the bevy of anomalously big and bright early galaxies was illusory, or could it have been flaws in the telescope's initial observations? But if these discoveries were genuine, could they be analyzed by standard cosmological models? Theorists also thought, could these discoveries be the first hints that the universe is more strange and complex than even our boldest theories had supposed? One thing this discovery made by the JWST puts at stake is our understanding of how the universe we know emerged from prehistoric chaos. This means that the JWST's early discoveries could be a factor that would rewrite the opening chapters of cosmic history, which does include not only distant epochs and faraway galaxies, but also human existence here in our familiar Milky Way. A senior advisor for science and exploration at the European Space Agency, Mark Makorian, commented on the discoveries made by the JWST. He stated, "You build these machines not to confirm the paradigm, but to break it. You just don't know how it will break." The JWST's observations of early galaxies have been billions of years in the making, but honestly, they only trace back to the Space Telescope Science Institute, STSCI, in 1985. At this time, the JWST's predecessor, the Hubble Space Telescope, was still 5 years away from launching on a space shuttle. But Garth Illingworth, the then deputy director of the STSCI, was surprised when his boss, director Riccardo Giacconi, who passed away in 2018, asked him a weird question. Giacconi asked his deputy about what would happen next after the Hubble Space Telescope made its discoveries. Illingworth was shocked at the question as he protested there was still much work to do on the Hubble Space Telescope, but Giacconi didn't budge. After that conversation, Illingworth put together a team and they began to draw up concept ideas for what they referred to as the Next Generation Space Telescope, NGST, later renamed the James Webb Telescope after former NASA administrator James Edwin Webb. And the need for the JWST telescope was made pressing in December 1995 when astronomers pointed the Hubble Space Telescope at a seemingly empty patch of sky for 10 days in a row. Several experts predicted the Hubble observation for 10 days would yield nothing much, and at its best would reveal some dim galaxies. But the results from the Hubble Space Telescope shocked them. This image, known as the Hubble Deep Field, showed that the empty spot it was pointed to contained thousands of galaxies dating back to 12 billion years into the 13.8 billion year history of our universe. Illingworth, now an astrophysicist at the University of California, Santa Cruz, recalled the discovery, saying there were galaxies everywhere. With that image, the Hubble field showed that the early universe was more crowded and exciting than most scientists had expected. It became a lost but now found treasure to astronomers and scientists who took the time to look properly. Despite how mind-blowing Hubble's deep field was, astronomers and scientists still wanted more, and that led to the birth of the James Webb Telescope. After over 2 decades of hard work and innovation at the cost of $10 billion, the James Webb Telescope was launched on December 26, 2021. Its journey started and it reached its deep space destination a month later. At this stage, the JWST had to go through powerful testing to ensure its optimal performance. This testing continued till July 2022, when it was ready to start its first year of science observations, which scientists titled Cycle 1. Parts of these early observations were dedicated to high-impact programs across several disciplines from which the data would be publicized immediately. 2 of these disciplines, SEERS, the Cosmic Evolution Early Release Science Survey, and GLASS, the Grissom Lens Amplified Survey from Space, independently spent dozens of hours looking for galaxies in the early universe by staring at separate small portions of the sky. Scientists didn't expect much from the JWST. At most, they expected a clearer version of the Hubble Deep Field, with the detection of extremely distant galaxies to pop up after a few cycles of data from multiple programs. However, the James Webb Telescope immediately showed its worth, as the first sets of observations made brought about the galaxies in the images spotted by Naidu and other astronomers in research groups. The influx of scientific papers about the JWST's initial observations was no accident, because as the first data began streaming down, astronomers and theorists started to write scientific papers and theories about their discoveries. But some scientists looked at the idea of having numerous scientific papers over the first sets of observations with concern. Klaus Pontoppidan, JWST's project scientist at STSCI, expressed his concerns, saying people in research groups might have rushed things a little bit. He gave his reasons, saying that early collaboration issues with JWST, for example, may have affected some results. Nathan Adams at the University of Manchester in England and his colleagues found dramatic changes could occur, with one galaxy at a redshift of 20.4 recalibrated to a redshift of just 0.7. However, these issues are not likely to eradicate JWST's high redshift galaxies, given their total number. Because of the number of galaxies seen and reports made by the scientists who discovered them, the odds of all scientific reports being wrong are small. As a result, scientists are looking to conduct follow-up observations with the James Webb Telescope. As a matter of fact, several research groups are sending proposals requesting more time to use the James Webb Telescope for space observations. The majority of these proposals seek to scrutinize high-redshift galaxy candidates. Regardless, more programs are set to kick off in the hunt for distant galaxies. One such program is the Cosmos Webb project. The mission is expected to increase the known populations of early galaxies by observing a wide sector of the sky for hundreds of hours, maybe a whole month or more. Scientists believe that thousands of galaxies out there are yet to be detected, and this mission would find them. There are several theories trying to explain how the universe started. They include the steady-state universe, which denies the possibility of a beginning and end for the universe, but says the universe is continuously expanding while still maintaining the same overall density. In other words, a steady-state universe is forever identical, but continually growing bigger in scale. In this model, galaxies, planets, and other forms of matter are locked in continual recreation. Since the density remains the same, old astronomical objects become unobservable as new creations take their place. Another competing theory is the bouncing cosmology or Big Bounce model, which says the universe shrinks to a minimum volume and then bounces back into a subsequent expansion. There is no shortage of theories of how the universe began, so there is the plasma or electric universe model. Plasma is the word given to the fourth state of matter, that is solid, liquid, gas, and plasma. A plasma is a gas that is so hot that some or all of its constituent atoms are split up into electrons and ions, which can move independently of each other. In plasma or electric universe theory, plasma takes up an integral role in cosmological events and the fundamental order of the universe, proposing electric currents that flow along plasma filaments capable of shaping and powering galaxies. These currents stream into stars, powering them like fluorescent bulbs and inducing the births of planets. There are more theories about how the universe began, but the most popular one is the Big Bang, and you can thank the popular TV show The Big Bang Theory for bringing it further to the masses. It is also the most widely accepted in the scientific community. This theory was born of the observation that other galaxies are moving away from our own at great speed in all directions, as if they had all been propelled by an ancient explosive force. A Belgian priest named Georges Lemaitre was the first to suggest the Big Bang Theory in the 1920s, when he theorized that the universe began from a single primordial atom. The idea received significant boosts from Edwin Hubble's observations that galaxies are speeding away from us in all directions, and from the 1960s discovery of cosmic microwave radiation, interpreted as echoes of the Big Bang by Arno Penzias and Robert Wilson. Further work has helped clarify the Big Bang's tempo. Here is how the Big Bang went. In the first 10 raised to the power of minus 43 seconds of its existence, the universe was very compact, less than a million billion billionth the size of a single atom. It is thought that at such an incomprehensibly dense, energetic state, the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were forged into a single force. Still, current theories haven't yet figured out how a single unified force would work. To pull this off, we'd need to know how gravity works on the subatomic scale, but currently we don't. By the time the universe was a billionth of a second old, the universe had cooled down enough for the four fundamental forces to separate from one another. The universe's fundamental particles also formed. It was still so hot that these particles hadn't yet assembled into many of the subatomic particles we have today, such as the proton. As the universe kept expanding, this piping hot primordial soup, known as the quark-gluon plasma, continued to cool. Some particle colliders, such as CERN's Large Hadron Collider, are powerful enough to recreate the quark-gluon plasma. The radiation was so intense in the early days of the universe that colliding photons could form pairs of particles made of matter and antimatter, which is like regular matter in every way, except with the opposite electrical charge. It is thought that the early universe contained equal amounts of matter and antimatter, but as the universe cooled, photons no longer packed enough punch to make matter-antimatter pairs. So, like an extreme game of musical chairs, many particles of matter and antimatter paired off and annihilated one another. Some excess matter survived, and it's now the stuff that people, planets, and galaxies are made of. Our existence is a clear sign that the laws of nature treat matter and antimatter slightly different. Researchers have experimentally observed this rule imbalance called CP violation in action. Physicists are still trying to figure out exactly how matter won out in the early universe. While scientists talk with confidence about what happened after the Big Bang, what exactly took place before the Big Bang? We will soon get to that after answering these two interesting questions related to the Big Bang. Where did the Big Bang take place? When a stick of dynamite explodes, the detonation occurs in one place, and shrapnel flies into the void. However, in the Big Bang there was no center and no pre-existing void, so it didn't happen at any location per se. Space itself popped into existence and began expanding everywhere at once. Some astronomy books compare the universe to a rising cake, with raisins representing galaxies. As the cake grows, raisins recede from each other with no center of expansion, just like the Big Bang. But, of course, a cake has an edge, unlike the universe, which may go on forever. In the real sense, no analogy can perfectly capture the Big Bang. Also, was the Big Bang a one-off? Well, at the beginning of the Big Bang, there was the inflationary vacuum. When it doubled its volume, it doubled its energy. When it tripled its volume, it tripled its energy. If banknotes were like this and you pulled apart a stack, ever more would appear. Physicists call inflation the ultimate free lunch. The inflationary vacuum expanded ever faster, but it was a quantum thing, and quantum things are fundamentally unpredictable. Randomly, all over the inflationary vacuum, parts of it decayed into an ordinary, everyday vacuum. The Big Bang is the story of how we got here and how the universe got started. And while a lot has been said about the Big Bang, what exactly happened before it? What existed in what form and for how long? This is one of the reasons scientists are excited about the JWST, because it's the only tool that can allow us to see billions of years into the past, enough to have a peep behind the Big Bang. But what exactly is singularity? Singularity, also known as the Planck epoch or Planck era, was the earliest known period of the universe. At this time, all matter was condensed on a single point of infinite density and extreme heat. During this period, it is believed that the quantum effects of gravity dominated physical interactions and that no other physical forces were of equal strength to gravitation. This Planck period of time extends from point 0 to approximately 10 raised to the power of negative 43 seconds, which can only be measured in Planck time. The extreme heat and density of matter rendered the state of the universe highly unstable. It thus began to expand and cool, leading to the manifestation of the fundamental forces of physics. From approximately 10 raised to the power of negative 43 seconds to 10 raised to the power of negative 36, the universe began to cross transition temperatures. It is here that the fundamental forces that govern the universe are believed to have started separating from each other. The first step in this was the force of gravitation separating from gauge forces, which account for strong and weak nuclear forces and electromagnetism. Then from 10 raised to the power of negative 36 to 10 raised to the power of negative 32 seconds after the Big Bang, the temperature of the universe was low enough at 1028 Kelvin that the forces of electromagnetism or strong force and weak nuclear forces or weak interaction were able to separate as well, forming two distinct forces. This was followed by the inflation epoch, lasting from 10 raised to the power of negative 32 seconds in Planck time to an unknown point. Here, the universe was filled homogeneously with a high energy density, and the incredibly high temperatures and pressure gave rise to rapid expansion and cooling. This began at 10 raised to the power of negative 37 seconds, where the phase transition that caused the separation of forces also led to a period where the universe grew exponentially. It was also at this point in time that baryogenesis occurred, which refers to a hypothetical event where temperatures were so high that the random motions of particles occurred at relativistic speeds. As a result of this, particle-antiparticle pairs of all kinds were being continuously created and destroyed in collisions, which is believed to have led to the predominance of matter over antimatter in the present universe. After inflation stopped, the universe consisted of a quark-gluon plasma, as well as all other elementary particles. From this point onward, the universe began to cool and matter coalesced and formed. Next was the cooling epoch, where the universe decreased in density and temperature, and the energy of each particle began to decline. Phase transitions continued until the fundamental forces of physics and elementary particles changed into their present form. Since particle energies would have dropped to values that particle physics experiments can obtain, this period onward is subject to less speculation. This was then followed by the structure epoch, which expands over billions of years down to our day. The slightly denser regions of the almost uniformly distributed matter of the universe began to become gravitationally attracted to each other. They therefore grew even denser, forming gas clouds, stars, galaxies, and the other astronomical structures that we regularly observe today. It was during this time that the modern universe began to take shape. This consists of visible matter distributed in structures of various sizes, ranging from stars and planets to galaxies, galaxy clusters, and superclusters, where matter is concentrated, that are separated by enormous gulfs containing few galaxies. But you may be asking, where did the Big Bang take place? That is a fair question, because if you hear an explosion outside, you may be fairly accurate in pinpointing the spot where it occurred. So can we travel to the spot in the universe where the Big Bang took place? Perhaps scientists can find a huge crater somewhere in the universe that corresponds to the ground zero of the event. The fact is that there is no such spot anywhere, because there is no exact spot where the Big Bang happened. The Big Bang actually happened everywhere, if that makes sense. Never mind that the term Big Bang conjures up explosions or detonation. Meanwhile, even though the Big Bang theory is widely accepted, it is not without its critics. There are some unresolved issues when scientists try to explain the beginning of the universe with the Big Bang theory. The first is the horizon problem. You see, there are portions of the universe that are visible to us but invisible to each other. Horizon problem says that different regions of the universe have not yet contacted each other due to the great distances between them, even though they have the same temperatures and other physical properties. We know that CMBR is found to be homogeneous everywhere. So how is this possible? The observed isotropy of the CMB is the problem in this regard, because we believe that information is not supposed to travel faster than light. However, the resolution of this apparent inconsistency is offered by inflationary theory, in which a homogeneous and isotropic scalar energy field dominates the universe at some very early period. According to Heisenberg, there were quantum thermal fluctuations during the inflationary phase, which would be magnified to cosmic scale. These fluctuations functions as the seeds of all current structure in the universe. Inflation predicts that the primordial fluctuations are nearly scale invariant and Gaussian, which has been accurately confirmed by the measurement of the CMBR. The instant before inflation began, the universe was only about 10 raised to the power of minus 24 centimeters in diameter. All matter and energy were in close and uniform contact within the briefest instant. The universe then expanded exponentially by a factor of about 10 raised to the power of 50, sending once intimately connected matter and energy to the farthest reaches of the universe. The information contained in the pre-inflationary universe didn't have to travel the speed of light, it traveled at the speed of inflation. Another problem with the Big Bang theory is known as the flatness problem. The thing is, according to Einstein's field equations of general relativity, the structure of space-time is affected by the presence of matter and energy on small scales, making space appear flat. This is just like how the surface of the Earth seems flat if one is looking at a small area, but on a large scale, space becomes bent by the gravitational effect of matter. The amount of bending or curvature of the universe depends on the density. What about the events that preceded the Big Bang? Humans are curious and are not satisfied with knowing only what happened post-Big Bang. We want to know what occurred before the event that started it all. This is not an easy thing to do, however. For instance, the cosmic dark ages prevent us from traveling back in time to see what happened during the Big Bang. The cosmic dark ages were a time when the universe was enveloped by a fog of neutral hydrogen that trapped the light of the first stars and galaxies. The fog didn't lift until 1 billion years after the Big Bang, when the neutral hydrogen had been reionized and once again split apart. Because light couldn't escape its surroundings during the Dark Ages, it couldn't journey outward through the universe to hit our detectors here on Earth nearly 13 billion years later. Even before that, there wasn't much light before the first stars formed, because aside from hydrogen atoms, most of the universe was made up of dark matter which doesn't emit light. So how do we leap over these dark periods and go right past the Big Bang to see what happened then? Where did all the initial energy come from? This is basically like trying to answer the question of who were you before you were born? This is where Stephen Hawking stepped in. Hawking regularly blew our minds with his theories on what happened and what's to come in our universe. For instance, he explained how we humans might have about 100 years left on Earth. He also predicted the Earth would become a nice ball of fire within about 600 years. Anyway, we are talking about the less doomsday-esque scenario of what happened before the Big Bang. Here is how the brilliant physicist approached it. There ought to be something very special about the boundary conditions of the universe, and what can be more special than the condition that there is no boundary? Stay with us, it gets more interesting from here. The no-boundary proposal, which Hawking and his frequent collaborator James Hartle fully formulated in a 1983 paper, envisions the cosmos having the shape of a shuttlecock. Just as a shuttlecock has a diameter of 0 at its bottommost point and gradually widens on the way up, the universe, according to the no-boundary proposal, smoothly expanded from a point of 0 size. Hartle and Hawking derived a formula describing the whole shuttlecock, the so-called wave function of the universe that encompasses the entire past, present and future at once. This renders moot all contemplation of seeds of creation, a creator, or any transition from a time before. Hartle and Hawking's proposal radically reconceptualized time. Each moment in the universe becomes a cross-section of the shuttlecock. While we perceive the universe as expanding and evolving from one moment to the next, time really consists of correlations between the universe's size in each cross-section and other properties, particularly its entropy or disorder. Entropy increases from the cork to the feathers, aiming an emergent arrow of time. Near the shuttlecock's rounded-off bottom, though, the correlations are less reliable. Time ceases to exist and is replaced by pure space. As Hartle explained it recently, we didn't have birds in the very early universe, we have birds later on. We didn't have time in the early universe, we have time later on. Hawking himself wrote about time. Events before the Big Bang are simply not defined because there's no way one could measure what happened at them. Since events before the Big Bang have no observational consequences, one may as well cut them out of the theory and say that time began at the Big Bang. On a Neil deGrasse Tyson show, Hawking also said, "Nothing was around. The Euclidean space-time is a closed surface without end, like the surface of the Earth." He said, "One can regard imaginary and real time as beginning at the South Pole, which is a smooth point of space-time where the normal laws of physics hold. There is nothing south of the South Pole, so there was nothing around before the Big Bang." Hawking and Hartle considered the possibility that the universe began as pure space rather than dynamical space-time, leading them to the shuttlecock geometry. They defined the no-boundary wave function describing such a universe using an approach invented by Hawking's hero, the physicist Richard Feynman. In the 1940s, Feynman devised a scheme for calculating the most likely outcomes of quantum mechanical events. To predict, say, the most probable results of a particle collision, Feynman found that you could sum up all possible paths that the colliding particles could take, weighting straightforward paths more than convoluted ones in the sum. Calculating this path integral gives you the wave function, a probability distribution indicating the different possible states of the particles after the collision. In the final years of his life, to better understand the wave function more generally, Hawking and his collaborators started applying holography, a new approach that treats space-time as a hologram. Hawking sought a holographic description of a shuttlecock-shaped universe in which the geometry of the entire past would project off of the present. That effort is continuing in Hawking's absence. For the past year, Neil Turok and his Perimeter Institute colleagues Latham Boyle and Kieran Finn have been developing a new cosmological model with much in common with the new boundary proposal. But instead of one shuttlecock, it envisions two arranged cork to cork in a sort of hourglass figure with time flowing in both directions. While the model is not yet developed enough to make predictions, Its charm lies in the way its lobes realize CPT symmetry, a seemingly fundamental mirror in nature that simultaneously reflects matter and antimatter, left and right and forward and backward in time. One disadvantage is that the universe's mirror image lobes meet at a singularity, a pinch in space-time that requires the unknown quantum theory of gravity to understand. Boylefen and Turok take a stab at the singularity, but such an attempt is inherently speculative. This explanation of the pre-Big Bang period by Hawking has been fascinating and inspiring physicists for years now. They find it stunningly beautiful and provocative. It was basically the first guess at the quantum description of the cosmos or the wave function of the universe. Soon, an entire field, quantum cosmology, sprang up as researchers devised alternative ideas about how the universe could have come from nothing, analyzed the theory's various predictions and ways to test them, and interpreted their philosophical meaning. The no-boundary wave function was, in some ways, the simplest possible proposal for that. Or perhaps there was something else before the Big Bang that is worth pondering. One idea is that the Big Bang isn't the beginning of time, but rather that it was a moment of symmetry. In this idea, prior to the Big Bang, there was another universe identical to this one, but with entropy increasing toward the past instead of toward the future. Increasing entropy, or increasing disorder in a system, is essentially the arrow of time, Carroll said. So in this mirror universe, time would run opposite to time in the modern universe, and our universe would be in the past. Proponents of this theory also suggest that other properties of the universe would be flip-flopped in this mirror universe. For example, physicist David Sloan wrote in the University of Oxford Science blog that asymmetries in molecules and ions, called chiralities, would be in opposite orientations to what they are in our universe. At any rate, another theory holds that the Big Bang wasn't really the beginning of everything, but rather a moment in time when the universe switched from a period of contraction to a period of expansion. This notion suggests that there could be infinite Big Bangs as the universe expands, contracts, and expands again. So to summarize, the Big Bang theory is the leading explanation for how the universe began. And in its most simple form, it says that the universe as we know it started with an infinitely hot and dense single point that inflated and stretched, initially at unimaginable speeds and then at a relatively measurable rate over the next 13.8 billion years to the still expanding cosmos we see today. So far, the Big Bang is our best guess about the origins of our universe. But now it seems that these new images from the JWST are making some scientists doubt the credibility of this theory. The Big Bang theory has been defended for multiple decades as an unquestionable truth by most cosmological theorists, but the new data from the JWST is making ones like Alison Kirkpatrick panic. She is an astronomer at the University of Kansas in Lawrence, and according to her, the latest revelations have made her question whether everything she's done in the field is wrong. The incredibly small, smooth, old, and surprisingly numerous galaxies are completely incompatible with the Big Bang hypothesis, in the opinion of a few scientists. The Big Bang proposes that the universe is expanding and a strange optical illusion must exist in outer space. Galaxies and other objects in the expanding space do not continue to look smaller with the increasing distance. Beyond a certain point, they start getting bigger, as their light is supposed to have left them when they were close to us. But the images of the JWST show them getting smaller and smaller. Even the galaxies with much greater luminosity and mass than our own Milky Way appear 2 to 3 times smaller in these images. In other words, the galaxies the JWST is showing us are the same size as the galaxies near us, indicating that the universe isn't expanding and that redshift isn't proportional to distance. The newer galaxies in the images have a redshift that is 2 to 3 times greater. This strongly contradicts the theory of an expanding universe, in the opinion of Eric Lerner and Ricardo Scarpa, but aligns with their prediction that we are part of a non-expanding universe. They had previously published results based on Hubble Space Telescope images that showed galaxies have a redshift all the way up to 5 that matched the expectations of non-expanding ordinary space. They were confident that the James Webb would only confirm their hypothesis. Big Bang theorists had expected to see badly mangled galaxies scrambled by multiple collisions and mergers. However, the JWST images actually showed overwhelmingly smooth disks and neat spiral forms, just like we see in today's galaxies. The data in the Panic article shows that there were around 10 times more smooth spiral galaxies than predicted, and this challenges our ideas about mergers being a very common process. According to Lerner and Scarpa, this data utterly destroys the merger theory. The Big Bang theory implies that the most distant galaxies in the James Webb images are seen as they were about 400 to 500 million years after the origin of our universe. But some of the galaxies have shown stellar populations that are at least 1 billion years old. Now, according to the Big Bang theory, nothing could have originated prior to it, so the authors of the Panic article believe that the existence of these galaxies is proof that the Big Bang didn't occur. And just as there must be no galaxies older than the Big Bang, so theorists expected that as the JWST looked out further in space and time, the galaxies would become fewer and eventually there would be none left, signifying a dark age in the cosmos. But a paper yet to be published demonstrates that galaxies as huge as the Milky Way are common even a few 100 million years after the hypothesized Big Bang. From the Big Bang standpoint, the distant galaxies are supposed to be intrinsically smaller. One galaxy noted in the papers is GHZ2, and it is far more luminous than the Milky Way and yet is calculated to be just 300 light-years in radius. This is 150 times smaller than the Milky Way. And the JWST images aren't the only reason the Big Bang theory may be considered wrong, according to Lerner. He believes that right now the Big Bang makes 16 wrong predictions and only one that is correct. Its prediction of helium is off by a factor of 2. The prediction of the abundance of lithium is off by a factor of 20. And besides the absence of larger and more distant optical illusions, there is also the existence of large-scale structures too big to have formed in the time since the Big Bang. Most cosmologists and astronomers have stated that there's an explanation for every doubt Lerner and Scarpa's article has raised. The Big Bang is definitely not dead, and the recent observations of the JWST haven't disproven the theory. These observations have revealed some unexpected and strange things about the universe, but that's all. The Big Bang is centered around 2 facts. First, that more distant galaxies have a higher redshift than closer ones, and second, that the universe is filled with a cosmic background of microwave radiation. These constitute 2 of the 3 pillars of data supporting the Big Bang theory, the third one being the relative abundance of elements in the early universe. But these are just the foundation of the model. In past years, scientists have expanded on these to create the standard model of cosmology, also called the LCDM model. Everything from acceleration of cosmic expansion to the clustering of galaxies support this model. The Tolman test predicts that if the universe was non-expanding and static, the surface brightness of all the galaxies would be the same regardless of the distance, which isn't the case as evident by the JWST images. The distant galaxies have a dimmer surface brightness than the closer ones in these images. It is a common misconception that redshift proves that galaxies are speeding away. They aren't in reality. Distant galaxies aren't speeding through space. In fact, space itself is expanding and thereby putting greater distance between us. This subtle difference emphasizes that the galactic redshift is a result of cosmic expansion and not relative motion. Experts aren't denying that what the James Webb Space Telescope found doesn't entirely align with their predictions, but astronomers were hoping to find this sort of puzzling data. They believe that is the reason why so much was invested in building the James Webb Space Telescope in the first place, and they understand that the data collected by this magnificent telescope doesn't tell us that the Big Bang model is wrong, but some of their assumptions about it could be.